Okay, so it's my pleasure to introduce our second speaker today, Laura Groves. She's a graduate student originally from Newfoundland, Canada. She completed her bachelor's degree majoring in animal science at Dalhousie University in Nova Scotia in 2018. And she began her master's at Atlantic Veterinary College in PEI in September of 2020 under the supervision of Dr. Mark Fast. So thanks very much, Laura, for joining us today, and you can take it away.
Hey, thanks for having me. So today I will be presenting on infectious salmon anemia and climate change, the combined effects on Atlantic salmon's immunological response. So there are multiple collaborators and people involved with this project, such as Dr. Shona White, the project manager, Dr. Sarah Purcell, the lab supervisor, Kathleen Parrish and John Pereira, who are master students, Dr. Amber Garber, who is our collaborator from Maui East, and of course, Dr. Mark Fast, who is my supervisor. Oh, 1 sec, it's trying to change the slides. Okay, so climate change and ISA. Ocean temperatures are expected to rise 1 to 4 degrees Celsius over the next 80 years. When temperatures are above 16 degrees Celsius, Atlantic salmon tend to become stressed and eat less, resulting in a decreased growth. Typically, over the course of a year, they're grown, the temperatures range from 4 to 18 degrees Celsius, with their optimum being around 10 to 12 degrees Celsius in the spring and the fall. So this will have a significant impact on the ability for the Atlantic salmon's immune system to fight off ISA. And in Canada, it costs producers millions in losses each year. So what is infectious salmon anemia? So mortality for this virus can range from 0.5 to 1% a day, and then it can have an overall death rate of up to 90%. In Canada, the normal practice is to cull any fish that may have been exposed on a farm. Net pens within 5 to 6 kilometers can become contaminated, so that is the method of control for this virus. There is currently no cure, but there are some vaccines that do exist, but there's little data on the actual efficacy rates of those vaccines. So some clinical signs are fluid accumulation in the body cavity, hemorrhage in internal organs, a dark liver, anemia such as pale gills, which you can see in the diagram on the right, decreased appetite, lethargy, and surface gasping. You can also see the congested liver on the diagram on the right. So circulation is affected due to damage to the cell membrane of the red blood cells as well. So the objective of my research, the current is to examine 20 distinct family backgrounds representing Maui East breeding program and their natural resistance and vaccine-induced resistance to ISA under multiple temperature regimes. So currently we did the study at 10 degrees and 20 degrees Celsius. This will allow Maui to select brood stock that have a better immunological response against infectious salmon anemia in higher ocean temperatures based on their molecular markers. So for my study design, there was 20 distinct families, as I mentioned, and each fish, there was 100 fish from each family. So half of the fish in each family were vaccinated with microforte vaccine, and half of the fish were given a placebo injection. The fish were divided into 38 tanks once they arrived at the Atlantic Veterinary College, with 2 fish from each family being placed in each tank. One of those fish was vaccinated and one of them was given the placebo injection. So as well, there was 250 donor Atlantic salmon, which were IP injected with the ISA isolate. So 1 week after this injection, 6 donors were added to each of the 38 study tanks. This is just a picture of the setups of one of the rooms that we have here at ABC. So we had 3 sampling time points for this study. For time one, we had 6 vaccinated and 6 placebo-injected fish from each family were sampled at 1,074 degree days post-vaccination. So protection for this vaccine was said to be given at when they were above 500 degree days. So time 1 was sampled 8 tanks at both temperatures were randomly sampled after the donor fish died and multiple mortalities occurred in cohabitants. And time 2 occurred 1 week after no mortalities occurred. So I just have a study timeline here because it gets a bit confusing. So originally the fish were acclimated and pit tagged. When they were 10 to 25 grams in size, they were vaccinated. And after 1,074 degree days, they were sampled for time 1. So after 2 weeks, they were transported to ABC and divided into their 38 tanks. They were given 3 weeks to then acclimatize, and then the donor fish were injected with the ISA isolate. 1 week after that, 6 donor fish are added to each of the 38 tanks. And then 20 days later, time 1 sampling occurred in the 20 degrees Celsius tanks. And then it took 29 days before the 10 degree sampling occurred for the time 1. So then 20 to 21 days after that, time 2 sampling occurred at 20 degrees, and 34 days later, time 2, that should say time 1, sorry, first, it's a mistake there. And then the second was time 2 occurred at 10 degrees sampling. So here's a graph that shows the mortality across the temperature of the two different temperature points that we use. So the x-axis shows days post-exposure, so after they were cohab with the donor fish, and the y-axis is the total mortality of the fish overall. What is interesting about this is the cold water. So the 10 degrees Celsius actually did worse. I would have kind of expected the 20 degrees Celsius to do worse. 22 degrees Celsius is the thermal limit for Atlantic salmon. So the fact that they did better at 20 degrees than they did at 10 was quite interesting. So it will be interesting to see the results for that. So they had about a 35% mortality overall. They're shown in the orange bars. And then the 10 degrees Celsius had about a 57% mortality overall. Whereas the 20 degrees Celsius, the mortality kind of dropped off a bit. So that is actually quite different than what I would have expected. So for our results, we decided to choose 6 families to start with to analyze, where we do have a lot of samples. So that's about, with the 6 families, about 400 samples that we're looking at. So we chose the families with the top 3 survival rates and the bottom 3 survival rates, the top 3 that did the worst and the top 3 that did the best. And between both temperatures, both 10 and 20, the families that did the best and the worst were the same for both. So you can see here for the 10 degrees Celsius, there's a bit more of a large range between the survival between the top and the worst families. And then it's a bit more spread out for our families at 20 degrees Celsius for the ones that did the best and the worst there. So currently we have done the ISA load for the time 1 samples. So any samples with a CQ value of 30 or greater were not included in our tables. So at 20, it's not shown here, but at 20 degrees Celsius, there were a higher proportion of fish that were negative for ISA. Compared to 10 degrees Celsius, the 20 degrees Celsius had more fish that showed that they had no ISA present in the sample. So there is some discussion on what the cutoff should be, whether they're positive or negative for ISA, but for our lab, we use 37 as the cutoff based on false positives that occur. So for our analytic methods, we're currently using the Luminex MEGPIC system. I was hoping to have some results for you guys for today, but unfortunately due to some shipping delays, we weren't able to get that for you. So I'm just going to go over how this system works because not everyone is familiar with it, and it is new to me as well. So it uses magnetic carboxylated polyester beads that can be coated with the antibody specific to the genes that you wish to analyze. And then once the RNA is added to each well, if the gene is present, it will bind to the specific capture antibodies on the magnetic beads. So a biotinylated specific antibody will then be added and bind to its respective gene already attached to an antibody on the bead. So then streptavidin is then added to each of the wells, which will bind to the biotinylated specific antibodies added in the previous step. The beads then attach to a magnet in a monolayer formation on the MEGPIC system. LEDs then illuminate the beads and a CCD camera takes a picture. So the system is able to determine if a gene was detected by a bead based on if there is an LED illuminated streptavidin present for each of the genes. So the streptavidin acts kind of like a flag to the system and it lights up if it's present. So then the system will then total how many beads in each well for each RNA sample lit up for each of the genes that the beads were coded with. And the final data for each is measured in mean fluorescent intensity for each gene. So for our study, we're using 17 genes that are on our viral multiplex. The genes that were chosen for this study were chosen based on looking at other studies and what genes of interest we should select, what they have found. So these are what we're going to start with. We have 3 reference genes as well, RPS20, EF1, and EIF3EA that we're using that's on our multiplex. So the 20 genes in total. I just highlighted 4 genes that I'm going to quickly discuss their function. So RIG1, the proposed function in Atlantic, slide skipped. The proposed function in Atlantic salmon is that it can detect viruses in their Orthomoxiviridae family. So ISA actually falls in the same family as influenza. So pro-inflammatory cytokines and type 1 interferons are produced in response to this gene, signaling a cascade. NKL, which a proposed function is cytotoxic activity, may begin as a result of it possibly being an effector molecule. MX1, the proposed function is stopping viral replication by blocking the amount of virus that can enter the cell and through decreasing MP synthesis. And SAA, proposed function is possibly induced by cytokine-like molecules. So we do have, just based on previous work in our lab, we have tested ISA exposed fish to controlled fish. And the ones that were infective showed a significant, as you can see, an upregulation in those genes that I just discussed. So RIG1 and NKL, you can see that the infected fish, there wasn't an upregulation in the genes. So we expect that there to be a difference between the families that did well and the families that did not so well. And same with these here. So we're hoping that we'll see a difference between the 2 families once we finish doing that data. So what's next? Once we finish, we're running time 0 and time 1 samples on the MEGPICs currently, and then we're running the time 2 samples on qPCR, and then we're having RNA sequencing completed. And from there, we're going to identify any further genes of interest to run on qPCR. So after we finish with the 17 genes, if there's any other genes that we want to look into, we'll do that from there. And those are my references, and that's all I have for today. So if you have any questions, you can go ahead and ask.
Great presentation, Laura. Thank you very much. We got plenty of time for questions. If folks have them, go ahead and unmute yourself, or you can drop them in the chat box for us. All right, Laura, you got a question here in the chat from John Drennan. He's curious, does the upper temperature threshold for ISAV have a possible impact on virulence and disease versus fish immune response?
I'm not quite sure what he's asking. The upper limit for ISA itself can do well up to 22 degrees. Same with the salmon's upper limit is 22 degrees, and in cell culture, ISA can also do well into 22 degrees. So for our study, we don't think that would the temperature would have effect on how well ISA does, if that's what you're asking, I think, because it still falls in the range of where the virus can thrive.
Okay, John, if you need clarification on that, either unmute
Yeah, that
yourself.
might not have been what you're asking.
Hi, Laura. I have a question for you. Great presentation, by the way. The gene expression studies that you presented towards the end, are those using the same model of cohabitation that you are using in this in your big experiment, in your vaccine experiment, or that is following injection? And the reason I ask is that for the gene expression, it's I don't know, how similar the response, from the different fish, will be, because with the cohabitation, they will be getting infected, not all of them at the same time, so that the expression itself, will be different, right? If they were injected, then all of them get the same bug at the same time, but might be a little bit more tricky to have a standardized levels in a cohabitation model. So I'm just curious if you have tried already to do this type of gene expression analysis in a cohabitation model of infection.
I haven't personally. I'm unsure if my lab may have. I've only started in September, so I'm only kind of getting into the depth of the research now. But I believe the graphs. The graphs here was just kind of to show how that there was a difference, but I think they would have been done in a cohab study as well, not like directly injected, because that wouldn't be how it occurs in the wild, whereas the cohab exposure is more relevant to how ISA would affect the fish in the wild.
Thank you.
Hi, Laura. My name is Gary Marty. I have a question for you. A recent paper attributed some of the lesions we've associated with ISA to Piscine reovirus, and I wondered if you considered a role of Piscine reovirus in your study. For example, are you testing it to ensure that your fish are free?
No, that isn't something that we have discussed, but I will. That is interesting, and I will look into that. You say it was a recent study?
Yeah, Hugh Ferguson was one of the co-authors on that paper. So if you talk to Dave Grillman, he would probably know about it.
Okay. And Dylan is in my lab, and he just said he believes, but he's not 100% sure that the qPCR data shown was done with the same cohabitation model, because this data was done before I arrived in the lab. So but he thinks it was done in the similar model as my project. Thanks, Dylan. Is there any other questions?
Hi, Laura. This is Joaquin. I have a question regarding the isolates you use for the experiment. If I recall, you use the HPR4 isolate. Have you ever or in your lab have you ever kind of tested other type of isolate that I'm not really familiar? I can't remember right now if the HPR4 is like endemic to Canada, but have you ever tried another one? Because usually this HPR isolate kind of change a lot their virulence. So yeah, that's my question.
I'm not sure if they've tried another isolate. They have used this isolate before. It was actually from, I would have to pull it up here, but from New Brunswick. I believe someone in New Brunswick, Dr. Gagne, maybe, that got the isolate from. They've used this isolate in studies before, but I'm not sure if my lab has used other isolates for ISA. I don't know if anyone in my lab that's in this discussion knows that or not, but this is the isolate that they've used here before.
All right, any additional questions out there?
I have lost sound on my call. I cannot hear anyone anymore. I don't know if anyone can hear me.
Yes, we can hear you.
Oh, wait, it's back in. Okay, someone just said something right before you said I can hear you. I didn't hear it.
I was just checking to see if there's any other questions out there.
Okay.
All right, without any,